We are continuing with chapter 22, and we are going to talk about assessing ventilation. So several respiratory volumes can be used to assess an individual's respiratory status. Respiratory volumes include things like the tidal volume, which is the amount of air that you move into and out of the lungs with each breath. These respiratory volumes can then be combined to calculate something called respiratory capacities, which can also give information on a person's respiratory status. Now, usually, whenever you come across an individual with a pulmonary disorder, their respiratory volumes and capacities are going to be abnormal. And in the past, we used something called a spirometer to measure respiratory volumes. However, a spirometer is cumbersome clinical tool, and basically it's huge, and it's about the size of a shop vac, like a medium small shop vac. I don't know if that means anything to you. It probably is about 5 to 7 gallons is what it would hold, but now we use electronic measuring devices. So respiratory volumes. We have a couple of pages on this, and the first one is tidal volume, and I just mentioned tidal volume on the last slide. And this is the amount of air that's moved into and out of the lung with each breath. It's about 500 mils. Then we have inspiratory reserve volume, and this is the amount of air that can be inspired forcefully beyond the tidal volume. Expiratory reserve volume is the amount of air that can be forcefully expelled from the lungs, and residual volume is the amount of air that remains in the lungs that's needed to keep the alveoli open. I did not ask any questions on respiratory capacities on your exam, so you do not need to know them, but you probably will need to know them for lab. I do want you to know that respiratory capacities are the combination of 2 or more respiratory volumes. This is just showing the different respiratory volumes and capacities. So we see cursor, can never find my cursor, thank you. Okay, tidal volume, up, down, just normal in and out, right? About 500 mils. Inspiratory reserve volume is the amount that you can forcefully inspire, goes way, way up. And then we have inspiratory reserve volume, expiratory reserve volume, which is a forceful exhale. And then I lost my cursor again. My goodness. It's going to be all about the cursor this semester. Then we have residual volume. And again, this is the amount of air that remains in the lungs and it's needed to keep the alveoli open. This is just showing you again the measurement, and it's just showing both respiratory volumes and respiratory capacities, and the values that you would expect with an average adult male and an average adult female, and then a description of each. Now we talk about dead space. And anatomical dead space does not contribute to gas exchange. It's just the air that remains in the passageways, about 150 mils out of the 500 mil tidal volume. Alveolar dead space is the space that's occupied by non-functioning alveoli. It could be due to collapse or obstruction of the alveoli. And then the sum of anatomical and alveolar space is dead space, is the total dead space. All right, now we're going to talk about gas exchange. So gas exchange does occur between the lungs and blood, as well as the blood and tissues. And in the very first video, maybe the second video, I don't remember right now, we talked about the fact that there is internal respiration and external respiration. And external respiration is going to be the diffusion of gases between the lungs and the blood. And internal respiration is going to be the diffusion of gases between the blood and the tissues. Both processes are subject to the basic properties of gas, as well as the composition of alveolar gas. And then we talk about Dalton's law of partial pressures. So now we're actually going to talk about some basic properties of gas. And then we're going to talk about Dalton's law of partial pressures. And this particular law states that the total pressure exerted by a mixture of gas is equal to the sum of pressures exerted by each gas. What this means is if you have a gas that's composed of, let's say air, for example, you have air, that's a gas, and air is composed of nitrogen primarily, then oxygen, then CO2, and then a number of other gases. But really when we talk, and then also some water vapor. But when we talk about air, usually we only talk about the nitrogen, the oxygen, the CO2, and then sometimes the water vapor is talked about. In any event, what it means is the pressure exerted by nitrogen, when added to the pressure exerted by oxygen, when added to the pressure exerted by CO2, and then the pressure exerted by the water vapor, is going to give you the sum total of the pressure of air. Okay? Partial pressure is the pressure exerted by each gas in a mixture. And you're going to see this represented by a big P and then a subscript of the gas. I'll show you what that is here in a second. It's directly proportional to its percentage in the mixture. All right, so what this means, we have air, and at sea level, atmospheric pressure is 760 millimeters of mercury. Nitrogen makes up about 78.6% of air. Therefore, the partial pressure of nitrogen, and this is what I was talking about here, partial pressure of nitrogen, this is how this is going to be denoted with a big P and then a subscript with the gas, can be calculated as follows. You take the whole pressure, the pressure of the entire gas, you multiply it by the percentage that that particular gas makes up, which in this case is 78.6%. You're going to get 597 millimeters of mercury due to nitrogen. Oxygen makes up 20.9%, so we do the same thing. 760 millimeters of mercury times 0.209 is going to give us 159 millimeters of mercury. Now, that added together is going to give us 756. So you can see we're still short a little bit, right? That's 756 out of 760, so we're still missing 4 millimeters of mercury. Air also contains 0.04% of CO2 and 0.5% of water vapor, and then insignificant amounts of other gases. At high altitudes, partial pressures decline, but at lower altitudes, partial pressures increase significantly. And this means like underwater. So on the next slide, we see this all worked out. Cursor. So we see that 597 again, we see that 159 again, and then the CO2 comes up with 0.3, and the water comes up with 3.7, and that gives us our 760 millimeters of mercury. So basically, these four gases, the partial pressures of those four gases added together are going to give us the total pressure of the gas. That's what Dalton's law is saying. That's all I have for you for this particular talk.